Here is an example where we have a collision happening kind of in the middle of our problem. So just try to, read through this. I want you to try to at least maybe think about what kinds of events you're going to have, events will you have, and also you can think about what technique or problem-solving technique or equations are you going to use to link up the different events that you have. So press pause, spend some time thinking about how you might solve this, and then press play when you want to go through it with me. Okay, so in terms of identifying events that are going to be important for this problem, I think it's obvious we're going to have one event when Tarzan starts from rest at the top of the cliff. And then there's going to be an event at the end when he's at the maximum height, this highest tree branch. The reason I know I want this to be an event is I know how high up he is, so I know how much potential energy he has. I know he's starting at rest, so I know how much kinetic energy he has. I know a lot about what's happening at this event. And then this is going to be my last event because this is what they're asking me for. What is the highest tree branch they can reach? That's like how high do they go? What's that maximum height? So this will definitely be an event because I want to know my height at this point in time. Now, if there were no collision here, then I could just say this is my initial and this is my final, and I would use conservation of energy. But there is a collision. Tarzan is going to swing down and he picks up Jane, and then they swing up together. That's a perfectly inelastic collision. And because there's a collision in between this event and this event, I need to break that up, and I need to have an event right before the collision and right after the collision. So this is actually going to be my event 0, this is my event 1, this is my event 2, and this is my event 3. Okay. Now in terms of what equations I'm going to use to relate the variables at this event to the variables at this event, I'm going to use conservation of energy, because I'm going to say that as Tarzan is coming down from that vine and swinging down, in this case the only forces that do work on him are conservative forces. The tension in that vine is not doing work because it's always perpendicular to the direction that he's moving. So the only forces that are doing work are conservative forces. That means mechanical energy will be conserved. That means that K0 plus U0 will have to equal K1 plus U1. This is right before the collision. This is when Tarzan is at the bottom of his swing. Okay. Now, when I relate what's happening before the collision to what's after the collision, I'm going to take the math, the numbers that I get here, and use conservation of momentum, because I'm looking at what happens right before the collision and what happens right after the collision. It's a perfectly inelastic collision, so my total momentum here, P1, has to equal my total momentum here, P2. Now, after the collision, I have these objects, they're traveling together, they're at their bottom of this, valley or whatever, and then they're going to swing up to a maximum height. And while they're swinging up to that maximum height, the only forces that are doing work on them are conservative forces, so mechanical energy will be conserved. So I'll use conservation of energy to relate all my variables at this point in time to my variables at this point in time. Okay, so that's just my planning. That's just how I think about it. And with these types of problems, it's very helpful to plan and think about it like that. So let's do it. I know I'm going to use conservation of energy to get from here to here, so I care about how much mechanical energy I have. My total mechanical energy is just my kinetic plus my potential. So in this case, the initial kinetic energy of Tarzan when he's starting from rest at the top of the cliff, his initial kinetic energy is 0. And his potential energy is going to be equal to his mass times g times his height at this event, which is 200 meters. So I find that initially Tarzan has 3,920 joules of energy. And that energy, in this case it's all potential, is going to get converted into kinetic energy, and that's going to allow me to figure out how fast he's going right before the collision. So I'm looking at my total mechanical energy before the collision. This is when he's at the bottom. He's 200 meters at the bottom, lower at this cliff. So now his potential energy here is 0 because his height is 0 at this event. And I know his mass, but I don't know his velocity. So I'm going to use conservation of energy and say that this much energy has to be equal to this much energy. Okay, so here's my conservation of energy. This is like K0 plus U0 equals K1 plus U1. There's my total mechanical energy when he's at the top. Here's my total mechanical energy when he's at the bottom. And that lets me calculate how fast he's going when he's at the bottom. So this V1, that's his velocity right before the collision. Now, I know that to figure out what's happening over here, I need to use conservation of momentum. So let's figure out what's happening with my momentum right before the collision. So this is my total momentum at my event number 1 right before the collision. It's equal to the momentum of Tarzan plus the momentum of Jane. That's the mass of Tarzan times the velocity of Tarzan before the collision, plus the mass of Jane times the velocity of Jane right before the collision. Tarzan is moving at 62.6 meters per second. Jane is at rest. So the total momentum of the system right before the collision is 125 kilogram meters per second. That means that my total momentum after the collision also has to be 125. After the collision, so this is at my event number 2, the two masses are moving together with one common final speed or velocity. So here's, I'm saying momentum has to be conserved, so the momentum I had at event 1 has to be equal to the momentum I have at event 2. And I find that after the collision, they're traveling at 41.7 meters per second. And now I know how fast they're going, so I can say they're going to have a certain amount of kinetic energy based on that velocity, and that kinetic energy is going to get converted into potential energy over here as they travel up. So here's my kinetic energy. I have to consider there's two masses, they're acting together now. They're stuck together, acting as one single mass, and they're traveling at 41.7 meters per second. So my total kinetic energy at this event, event number 2, is 2608 joules. There's no potential energy here, so this is also my total mechanical energy. Let's just compare that to how much mechanical energy Tarzan had up here. So we've lost kinetic energy. Sorry, we've lost mechanical energy. How much did we lose? We lost 3920 minus 2608. What did we lose it to? Probably friction. You know, when if he really smacked into her going that fast, she might, you know, like have bruises, which means that he's like broken, like, you know, blood vessels on her. That takes energy to break those things. So there's lots of places for energy to be lost in a collision like that. So this is going to be my total mechanical energy after the collision, because I have no potential energy because I'm at the bottom of the cliff. And all of this kinetic energy is going to get turned into potential energy as they go up higher and reach their maximum height. So here's my total mechanical energy at this event. Again, I have to treat the masses as one single mass because they're stuck together now. And when they reach their maximum height, their velocity is going to be 0, so that kinetic energy there is 0. So I can say my total mechanical energy at this maximum height is just due to their potential energy, and I don't know what that height is. That's what I'm trying to solve for. And then I can say the mechanical energy I have at this event has to be equal to the mechanical energy I have at this event because energy is conserved here. And then I can solve for my final height.